there's some more of those fabulous Apple TVs, so fill out your survey. So this morning we have two panels lined up for you guys about IPv6. This is the joint part of the ARIN NANOG meeting. So we're trying to talk first about mechanisms and then about experiences with deploying v6. And so I'm going to hand it over to Lee Howard.
Good morning. You have slides for me? The shared addressing issues slides. But while you're bringing those up, I'll do some introductions. My name is Lee Howard. I work for Time Warner Cable, and I also serve on the ARIN Board of Trustees. I hope you'll recognize my name when you vote later this week. I've put together a panel of people to talk about transition planning, what to do as you worry about how to handle the run out of IPv4 available address pool. And there are a variety of things that we can do about it. So what you do depends on what your requirements are. And so we put together, and I'm going to introduce them quickly. I have Jason Weil, who's going to talk about NAT44, large-scale NATs. I have Yu Lee, who's going to talk about dual-stack light. Steve Wright is going to talk about 6RD. He's going to talk about address family translation. And Masato Yamanishi is going to talk about 6RD. And I especially want to thank Yamanishi-san for stepping in at the very last minute. The presenter I had originally lined up lost his corporate support to present today. And so I was able to find somebody who has really excellent experience with 6RD and is able to share that with us because I think that we all need to see, again, what the considerations are for our various training possibilities. So thank you very much. If you don't have slides, I can bring my laptop up. But that's not the one I want to see. No. That's yours. I'm looking for mine. Because I had a couple of slides to talk about general issues. And I apologize for that. It is still fairly early in the morning on the third day of NANOG. So I have this little cartoon that I use to show executives what carrier-grade NAT, what address sharing looks like. So here we have a typical network with some NATs that have been injected into the middle of the large ISP. And a packet is an identifier, and it has a name attached to it. And if you change the name on that packet at multiple points along the path, then by the time the packet gets to its destination, you have no idea what that packet's name was. So that's the fun version for your executives. But here's a slightly more technical version. Most people in here probably know this already. This is, you got a source address and a destination address. You set up a mapping in each device along the path that's doing address translation and change the packet header as you're doing that translation. So what that means is when you have shared addresses, many people are going to be using the same IP address. So if you have, if somebody comes to you as a network operator and says, who was using address 192.0.2.117 at a given time, your response is going to be, I don't know. Thousands of people were using that address at that time. So you have to, you as the operator running this address sharing mechanism, whether it's carrier grade NAT or dual stack light or whatever, will have to say, I'm sorry, FBI or RCMP or MPAA, your subpoena is overly broad, I am unable to respond. And it turns out that, so part of the issue here is NAT, of course, is used in the home very commonly, all the time. Everybody has a NAT in their home. All right, maybe not everybody here. Many people have NAT in their home. But what the FBI is looking for when they serve a subpoena is which door to kick down. And if you say there are 1,000 doors behind which that address might be used, that's of no use to them whatsoever. So it gets a little bit worse. If you have a user, and of course none of my users would attack any of your users, but if you had a user on your network who was doing something malicious and somebody needed to report that abuse, then the the abuse report is not going to contain sufficient detail to identify the bad guy. So typically, web logs, mail server logs don't track the source port. And maybe your timestamp is reliable, maybe your NTP source is good, and maybe you're telling me whether you're using UTC, GMT, or EDT, but maybe not. And so just a few seconds of slip, depending on your address sharing settings, could really cause problems. And then somebody goes to protect their network and black holes thousands of users. If you're a content provider, you're black holing thousands of people who are trying to get to your content because one of them attacked you. That's potentially very problematic. So in the situation that I like to call NAT 44444, because that's how many times it gets translated, the user on one side, the PC or an end user subscriber on one side doesn't know the address on the other side. So subscriber here, in this picture we've got on the left, subscriber A is trying to reach subscriber B, goes to a tracker server, peer-to-peer, it uses a tracker server, maybe a game console, it's using somebody's game system live. And goes to the tracker server and says, please tell me the address of subscriber B, my buddy, who I want to play with. And the tracker server says, here you go, I know that IP address, I just got that connection. The IP address it sees is maybe the actual IP address of subscriber B, which is not reachable because it's a private address, or it may be the external address of the carrier grade NAT, which won't be usable to subscriber A because the state entry in that large scale NAT is based on the 5-tuple. So if subscriber A sends a packet to subscriber B, it doesn't match the 5-tuple because the original source destination address was based on that tracker server. So the communication fails. So, and this is true, again, the use case here is both peer-to-peer. Testing I've done says peer-to-peer seeding doesn't work and several online gaming systems don't work. Geolocation. If you are dependent on the IP address to determine geographically where somebody is so that you can provide them specific content, advertising for instance, and somebody's using a large-scale NAT, especially in early deployments, I think this scenario is likely, it's entirely possible that an ISP would say, I'm only going to have a few thousand users initially who I need to put by a large-scale NAT box. But those users, so I'm only going to buy one box, or maybe two for redundancy or something if they shared state, which would be nice. So now you have customers in New York, DC, Atlanta, LA, and San Francisco all behind the same address. Just trying to figure out where those users are coming from is going to be really complicated. So here's something I like to call port spray. When you're provisioning your large-scale NAT, how many connections, how many ports do you allocate that user? It's many, because a common website, CNN.com, opens more than 80 TCP connections in order to get all the content on their homepage. Some applications that we know of open hundreds of sessions for a variety of reasons. And what happens then if your browser crashes or you need to hit reload or something? All those session mappings are still open, so all those ports are still reserved because they haven't been FIN'd or RST'd, but you're opening new connections. How many ports can you reserve, and therefore how many users can you actually put behind a single address? I need to give credit to Matt Ford in particular of ISOC and the other people on this slide for their work on this internet draft. Many more issues with shared addressing are documented here. I just highlighted the ones that I think are most significant. So I refer you to that, and as always, great work from ISOC. Conclusions that I have: sharing addresses makes security hard. Lots of things make security hard, but in this particular case, subpoena response, there are many people using that, I can't identify that, and black holes affecting many customers, potential downsides. Sharing addresses breaks some applications, and maybe some people's response will be, well, we can work around that. We can develop stun, turn, ice. We can develop certain kinds of mechanisms, PCP, to work through carrier-grade NAT issues. But if you do that, I would argue you can develop that, or you can develop your IPv6 stack. And I think I know which way I would suggest you go. Sharing addresses makes operation support hard. Where do you put your monitoring system for customers who have private addresses? Do you need to have separate instances of monitoring behind each instance of NAT in your network? And of course, how many ports per user. One of the soundbite that I want to leave, and I should have made a slide for this, the soundbite that I want to leave before I hand off to Jason is to say your run-out date, the date at which you need IPv6, isn't necessarily the date that you run out of IPv4 addresses for new turnups. The date that you need IPv6 is the date somebody else deploys carrier-grade NAT and your users want to reach them. Thank you very much. Jason's going to talk more about specifically NAT 444.
So for those of you that don't know me, my name is Jason Weil. I'm a network architect at Cox Communications. I'm in charge of the V6 transition program there, technical lead for that program. So I'm going to talk today for a few minutes here about what NAT 444 is, what I like to call service provider NAT 444. Yes, I'm throwing in a whole nother term for yet something that has a lot of terms already. Some of those I'm sure you've heard in press and from vendors and whatnot, but there's NAT 444, which is somewhat confusing because there's basically it's NAT 444 in the service provider, but this implies that there's another layer of NAT 444 somewhere else, but I can see there's some confusion in that terminology. Large-scale NAT became pretty popular as well as carrier-grade NAT. I guess carrier-grade NAT had some negative connotations in some communities, so they opted for large-scale NAT. Now I'm throwing out yet another one called service provider NAT, SPNAT 4.4, because in reality what we're actually doing is NAT 4.4 somewhere within the service provider internal network. So let's start out comparing residential NAT 4.4 versus service provider NAT 4.4, because really for me that's the two NAT versions I'm dealing with, at least in the access provider network. So on the residential side, you have basic NAT 4.4 that's bounded by the home gateway, and then is serving addressing to the CE devices or consumer electronic devices within the home. Typically that uses RFC 1918. Actually, it always uses RFC 1918 from what I've seen. Either 192.168, that /16 block, or the 10/8, which is a little less common, but more problematic, as I'll get to later. One of the key differentiators here between service provider NAT and residential NAT is the current mapping for the public IP space to the home network is 1-to-1. So you have one public IP represents one household. So to differentiate that in service provider NAT, you have now a mapping of one IP public to multiple households private. And then there's multiple layers of, and that's where you get your second layer of NAT behind there. The other big challenge here is with standard residential NAT 4.4, you have the full address, the full port range, all 16 bits to use, so 65,000 plus ports. And you can do things like port forwarding and UPnP that actually utilize static ports within that range. With the service provider NAT, you lose that option, and now you're sharing the port availability, the 16-bit port availability amongst multiple households, which adds a layer of complexity. The other issue here is what address range to use within the service provider NAT. RFC 1918 is possible, but there's also other options like shared provider space. So here's a nice diagram that I borrowed from Jeff Doyle. Thank you very much for that if you're listening. So what this shows is basically what I just talked about before. You have the orange layer of private IP address space, which is the service provider NAT, bounded by the orange LSN and the CPE NAT on the bottom there. This is a good example of what it would look like on a fairly large network, because you're not going to, and I'll get into this in a minute, but you're not going to deploy, or I wouldn't think you'd want to deploy one massive NAT in the center of your network. You're probably going to want to deploy multiple smaller NATs, and then now you can limit the number of customers that are mapped to each NAT. And then on the bottom there, you have your standard residential NAT in gray, which is your standard RFC 1918 address space for home CE devices. All right, some considerations for deploying this in networks. So these are the two that I've come up with. The current model is the standard inline model, which is very typical in service provider enterprise networks, as well as the residential network, where all traffic is going through the NAT. You can differentiate traffic that you actually want to NAT going through that box within the box itself, but it does represent a single point of failure. The other option I like to call a NAT on a stick, where you're actually sticking a NAT off of your service aggregation layer routers, and then using source-based IP routing to get traffic to that, and then there's a nice default out back to your standard aggregation router. Lots of deployment considerations to consider. First off is just how to scale the box itself. Obviously, there's two big factors here: is capacity. How much? I mean, if you think of the average customer, at peak time, using possibly a meg or two. If you put a few thousand customers behind that, that's a good deal of traffic going through that box. The other issue is number of the memory requirements on that box based on the number of concurrent sessions you need to keep open, as well as the number of new sessions you have to open up at any given per second. Bigger issue, so that's fairly doable, standard architecture design there. The bigger challenge here is the logging, which is I'll reference some of the work Lee did, but the challenges from the law enforcement side. We actually have to maintain a mapping of the public IP to the private IP, which means we need to log a heck of a lot of state information in that box. So doing this when you're talking about possibly putting 30, 40 gig through one of these boxes is a lot of state to maintain. So it's some interesting considerations, and there's actually a draft in the IATF that's talking about some of this as well, of how to actually do it. And then the benefits of service provider NAT versus some of the other ones that we'll talk about today is that NAT is very well understood, at least NAT 4.4 is very well understood. It's been in use for, 8, 9 years at least within my home, so I'm pretty comfortable with the way it works. It also does not require, this is the biggest issue for me, is it doesn't require the replacement of the home gateway router. So for at least in the standard cable deployment today, we don't actually offer, we offer the home gateway now, but it's not an option that a lot of customers use. So the common scenario, and probably I'd say 80+% of homes, is they'll get out of service, you have a layer 2 cable modem there, and they're plugging in their home gateway. So those boxes today aren't going to support V6, so I have to do something to support those guys until we can get them to swap those boxes out. One of the other tangential benefits is it does enforce our acceptable use policy, and the fact that technically, if you're a standard residential customer, you're not supposed to run servers and act like a business out of your home. So that is one of the benefits. Unfortunately, that's the only benefit that anyway. All right, some of the challenges. I don't want to go too in depth here, but Lee's already covered a bunch of these. I'll just touch on the biggies, and the biggest is the fact that the whole mapping of multiple homes, and we're talking up to thousands of homes to one IP, causes all kinds of challenges for law enforcement, security, and spam, blacklisting, whitelisting. It's going to be a big issue going forward, especially. I know it's something the law enforcement is concerned about. Is all right. Now I need to know how to map I have somebody's spamming me, or there's a motion picture issue. Somebody's using copyrighted content they shouldn't be, but they're coming from this IP address. Well, that's not going to work because now that represents a whole neighborhood or a small city. So now you have to add more information to that collection effort. There's an address conflict issue here so you could use RFC 1918 space on that service provider realm. The problem here is if the residential NAT uses that same space, you now have an address conflict, and that's somewhat challenging to work through. So there are a couple options out there of how we can alleviate this. I actually have a draft I'm talking about later on another panel. And then there's a NTT Shirosaki draft is a similar proposal, but we'll talk about that later. It does break UPnP deployments, so obviously a lot of the home gaming consoles use this, so that's a problem. PS3 I know is a good one that breaks pretty well behind these devices, and we actually have done some testing in the labs to show what works and what doesn't. There are ways around this. The UPnP forum is looking to extend in their next option to support some of these some of this new functionality. I guess you could call it that. So, and there are port mapping protocols, a few options in IETF works underway as well. Obviously, there's a reduction in resiliency. You now have a single point of failure, which is uncommon in most service provider networks where you typically have multiple boxes serving as backup. So that's a problem. And then the security considerations that I've already talked about. All right, so 2 use cases here for this deployment. Getting close. All right, RIR. So the assumptions here are basic. RIRs are out of space. We have no more IPv4 address space. We're actually deploying V6. I think everybody I've talked to is going to be doing this. You're looking at V6 plus V4 deployment, but you need a way to extend your V4 address space. So use case 1 is a single stack IPv4. So the scenario here is either, like I was saying, you have the home gateways that are going to be V4 only, so you have to do something until you can either replace that yourself or the customer replaces it so you can support V6 to the home. The other one is the provider network segment. So we have a challenge in some portions of the network where access devices don't support V6 today. They will in the near future, so you need some interim ability to continue supporting between when you run out and when you can support V6 on those devices. So these are going to be small segmented deployments. The second use case is dual stack native IPv6 plus IPv4. What this does is supports the use case of customers that have V4 only devices, such as their large televisions that they're not going to replace any day soon, but they still want to get Netflix, Hulu, Pandora streamed to that television. Obviously, we have to support that and just not kill it with this device, or not kill it with IPv6 deployment. So this is a pretty good use case for that scenario. So conclusions, I see NAT, service provider NAT definitely being deployed. Hopefully it'll be deployed in small segments here and there where needed, and only as a interim device to get you to where you're having V6 native and migrating all your V4 customers to V6 as quickly as possible. Preferred topology for me is NAT on a stick, so it gets the box out of line, so if that box does fail, it's not going to take down any of your standard traffic. And then obviously we have some challenges with the shared addressing model that we'll talk about later on. And that's good. I'll save some time.
Hey, good morning, guys. My name is Yuli from Comcast. So I'm going to present you guys for the DS Lite. So before the presentation, this is what the company asked me to put in. So basically what I'm saying is I'm going to give you guys a brief overview for the transition technology. And then the transition technology is called DS Lite, which is try to standardize. I mean, it's already in the working group last call. It is now in the IES3. The presentation also gives you some test results. I think you guys are also interested how this technology works in the labs. And the goal here is try to give you guys some general understanding how these technologies work and then how you can deploy it in your network. And the disclaimer here is we heavily investigating the technology, but we are not committing to deploy it for the time being. So overview. So basically DS Lite is a transition technology. It tries to provide a dual stack to the user at home and then try to give a dual stack environment to the user at home, but we are not giving the user a real public IPv4 address. So similar to all, Jason and Lee present, we have a NAT in the network, but we are not doing a double NAT in this case. We basically saying is we have a tunnel from the home gateway to the carrier grade NAT in the network. And this allow the user, or allow the service provider to do an incremental upgrade for the IPv6 because now you really have, you have a motivation to deploy IPv6 because now you can save the IPv4 address. Very important for the DS Lite is day one when you deploy DS Lite, you give native IPv6 to the home. And you will also encourage the user and applications to go IPv6. This is not a technology to design to prolong IPv4. It's just basically give you a transition technology. So while you deploy IPv6, and we can provide the IPv4 service continuity to your home user. And because in the end, deploying a NAT in the network there's a cost associated to it, and then there's a capacity associated to it as well. So the technology works is I give a V6 address provision to the CPE, and then when the CPE receives the V4 packets, instead of doing a NAT today in the home network, you just basically encapsulate the packet into a V6 address, and then ship it to the home the carrier grade NAT, and then you decapsulate it and do a NAT there. So basically, you're just pushing the NAT from home to the service provider and try to utilize the port range and then share amount with different users. And DS-Lite is a tunneling technology, it's not a transition technology, because in IETF, they have a discussion like doing a tunneling technology and transition technologies. Even though according to this is transition technology in the whole saying they transition to V6, but the way to do it is actually tunneling the packet. So the big difference is the network is not touching the IP header. Instead, just encapsulate and decapsulate the packet. Normally, when you do translation, LET64 and NAT46, you're actually manipulating the IP addresses. So this is like the diagram, very high level, how it works. So the purple color is the dual stack. We expect the network will be dual stack. We also expect the home user at home will be dual stack. The green color meaning is only V6. So the CPE is only running V6, and you create a tunnel, which is yellow color, to encapsulate the packet into the tunnel endpoint. And then the tunnel endpoint and the NAT will become a one box called AFTR, Address Family Translation Router, which will do both the tunnel termination and the NAT44 functionality. So you combine two functions into one because we need the IPv6 address to become one of the entry of the NAT table. So I have the NAT table so there, and you would just do a simple translation from the inside local address to the inside global address. And it's work very similar to the current CPE at home. The only difference is now you're pushing the NAT to the network and you're running IPv6. And because you have IPv6 access network at this point, you can delegate a prefix to the home gateway, and the home gateway will give native V6 to the CPE. If your CPE, sorry, not CPE, I mean your host. If your host is still static, then you have a V6 address, and if you try to reach a V6 native site, then you will bypass all this infrastructure and then do native V6 all the way to the destination. So I think Jason already gave us some overview of the NAT444, so I'm not going to repeat it, but I want to give you guys some comparison between these two technologies. I mean, they have some similar characteristics, but they also have some different characteristics. So NAT444, the major advantage is you don't need to change the gateway. But DS-Lite you have to, because now you don't do NAT in the network, you actually create a tunnel from the CPE to the network. And the NAT444, in theory, if you only consider IPv4, you don't have to do a network upgrade, but in DS-Lite you have to, because this is the #1 priority. We want to give V6 as access network to create a tunnel so that we preserve the V4 addresses. In NAT444, there is no encapsulation overhead because you are doing a simple NAT. And DS-Lite, because you are doing an encapsulation, so you have to, MTU may cause a UE issue in some of the systems. So you have to consider if you're putting an extra 40 bytes in the header, then what happens to your applications. And NAT444 is a double NAT, and DS-Lite is not, because you're pushing the NAT from the home to the network, so you're still doing a single NAT. And NAT444, in theory, you only can support IPv4 by the technology. And DS-Lite is no, because day one you will have native IPv6, so you can support both IPv4 and IPv6. If your network is big enough, a single NAT10 cannot cover, then you may have to deploy multiple routing domain because you have multiple NAT10, we call it federated NAT10. So in this case, you will have to identify the user, which NAT10 network you are in, and you may have to create multiple routing domain. And this this is proven can get into some very compressed the network, the routing architecture. From DS-Lite, because we rely on the IPv6, it's just like MPLS. So you're using IPv6 more or less like access network. So that's why you will have a single IPv6 domain no matter where you put the net. And from the routing perspective, you are doing a native V6 packet, even for the encapsulation packet. So you only need to maintain a single IPv6 domain. So NetSplit may move clients to a different routing domain because of the situation I mentioned. If you have multiple routing domains, and you may have to identify, okay, which user I am, which routing domain I am in, and when you move the user, then you have to be careful when you do all this consideration. But for DS-Lite, when you split the client to a different NAT, all you have to do is, well, you know what, the NAT1, the AFTR1 now is running out of capacity. You just need to send a new DHCP option or radio options to the CPE saying that, okay, don't go to this NAT box anymore, go to a different one. And from the scaling perspective, then you can very easy to point a user to a different NAT without touching the routing domain. So these are some tests we have done in our lab to test it. Okay, if I have a DSLi running in our network, what kind of application I can run, and then what kind of application I may have problems. So web, HTTP, HTTPS one, no problem, because you can expect that this is a single NAT technology. So they will run today, they will run tomorrow. Same for email. This is on a single email and POP clients or IPsec VPN, a public IM using like Yahoo. I think we test Yahoo, Skype, AIM, MSN. I mean, pretty much all the public IMs. And then we test both video and text, it all works, no problem. Video streaming, it will work if if you try to go to Netflix to download a movie to watch it, or you go to ESPN Free to watch a sport game, it works, no problem. Peer-to-peer download and seeding also work over TCP, and I think it works today on your CPE, it will work tomorrow. But if it's only over TCP, because when you start using UDP, then you may have to do some hole punching on the CPE, which rely on UPnP. Then I will explain why the UPnP won't work later. We have tested also some multiplayer online games here. We tested like the more famous one, like Halo, Team Fortress, World of Warcraft. They work no problem. But I have to admit that we don't have all the games in our lab, and we have no intention to test every single game, because then they will fire me, because now I'm playing games in the office. So I mean, we only test all the famous ones. So don't blame me if, let's say, you try to test it in your lab and say, okay, it doesn't work. So I'm happy to see the result if you say which game doesn't work, and then we can work together to see why. But yeah, most of the games we test have no problem. And we also test it to go to Xbox Live. We can successfully connect to Xbox Live and then play the multiplayer games. Just like what Jason said, UPnP IGP is not going to work, because by the protocol itself, we always assume that you will have all the ports ring and the CPU will respond just yes or no. When you try to put it in the network, try to do a netting in the network and try to share the 65,000 port with among users, UPnP by default today is not working well. Some of the application request a specific source port, such as like you try to become a streaming server, try to streaming video from your home, or you try to do a gaming server, which may need to bind to a specific port. As we all know that, because now the port is shared by all the users, so you may not be able to ask for like port 10,000. So this is what I already expressed. So I'm not going to touch all the details. So one thing I want to point out here is IETF actually formed a new working group last time in Matrix. So it's called Port Control Protocol. This is trying to address the UPnP problem. But I think the thing is, this is a new protocol. It may not be able to be backward compatible to the existing UPnP. So all the applications still relying on the old UPnP, it may still not working. And I mentioned before that the specific, if you ask for a specific source port, it's not going to work. And this is not just a DSLi technology. Any technology sharing IPv4 addresses will have the same problem. So some rules may change. I'm also not going to touch the details, because Jason already mentioned it. So you have to now know what's the time, protocol, IP addresses, and port number in order to identify users. You also have to find a way to work if, let's say, an application now asks for a specific port, then how are you going to solve that problem? So if you don't want to deal with all this, the easiest way is just go IPv6, because you have IPv6 at the network. So conclusion. So DSLi is a technology, it's a technology, give a deal stack to the home user without giving an IPv4 address to the CPE. And then you will have IPv6 at home day one. DSLi is still new, and it's still developing in IETF, so you may have some changes in the future in the spec. So all the tests we have done now is just as of like September 2010. If any revisions comes, then we may have to revise the test, and then we have to test it again to see whether it works or not. So service provider, content provider, you have to prepare to identify user by port and IP, because now you cannot just identify user by port. And also, IPv6 is preferred, because if you don't have to do all this issue or don't have to deal with all that, and DSLi already give a v6 directly to the user day one. So last thing I want to give you guys is actually all the stuff I have done in the lab. You can download it. It's open source, ready. You can build it in the lab. If you have any problem, just let me know. I'm more than happy to help you guys to do it. Thank you.
Oh, sorry. My name is Masato Yamanishi, and I'm working in technology planning department of SoftBank Group. And to be honest, I'm not protocol specialist. The only reason I'm standing here is in last evening, Martin Levy of Hurricane Electric suddenly sent text which says, "I need you from 9 a.m. in tomorrow morning." So I said, okay, I'm sure, okay, yes, sir. so I'm standing here. Anyway, SoftBank is third largest carrier and one largest ISP in Japan, and we have currently two different access networks for broadband service. First one is ADSL-based access network, which was made almost 9 years ago, so it was quite old infrastructure. And second one is FTTH access network, which is newly developing recently. Then we choose 6LD for our ADSL access network. So today, let me explain why we choose 6LD for our ADSL access network. Anyway, we choose different solution for FTTH access network because it has different characteristics. Then this slide shows current situation of our ADSL access network. Then our ADSL access network is IPv4 only network. So it means replacing or upgrading old devices to enable IPv6 is not realistic. Actually, number of equipment is more than 10,000, so it's impossible. Also, we will need we need 6/4 technology to provide IPv6 connectivity for our customer. Then actually, subscriber on our ADSL service are moving to FTTH, so it means number of subscriber is slightly decreasing. So also, existing subscriber already have global IPv4 address, so we can use it for to provide IPv6 connectivity. Also, we are providing ADSL modems as CPE, so we can control their software. And last point is very important point. Nobody wants to pay for IPv6 transition, it's true. So we should minimize all costs enabling provisioning devices and maintenance or, like that, everything. We should minimize everything. Then there is a lot of text on right-hand side, but please omit it because it will be explained in later slide. But the point is, in 6LD, we have two different components. First one is relay router, which is located in our head end, and the second portion is CPE, which is located in user's home. Also, user's home network is dual stack, and of course external network is dual stack, but in access network IPv6 is not enabled, so we should pass this part by using 6LD. Then this slide shows how relay router and CPE can figure out v6 prefix. First of all, we are using 2001 DB8/32 as 6LD prefix. Then from this prefix, CPE can easily figure out its IPv6 prefix address. Actually, it needs 6LD prefix address and also global IPv4 address. On this slide, I'm using private IPv4 address, but actually we are using global IPv4 address. Then first 32, prefix address which will be assigned to each subscriber is determined by, first 32-bit is determined by 6LD prefix. It's just copy from it. And second 32-bit is copy of global IPv4 address, which is assigned for each subscriber. So it is very simple, and there's no provisioning for CPE. Then this slide shows how relay router and CPE proceed incoming packet. First of all, relay router, when receive IPv6 packet from outside, relay router check normal IPv6 routing table, and routing table says, okay, if first 32-bit match to 6LD prefix sends to tunnel interface, then tunnel interface checks second 32-bit 32-bit of destination IPv6 address, then extract it, then make it as destination IPv4 address. Sorry, I mixed IPv4 and IPv6 because it is very complicated. Anyway, so making IPv4 header is very simple. Just extracting second 32-bit of destination IPv6 address and make it to destination IPv4 address. Then send it based on IPv4 routing table. So it's very simple and stateless. So it means it is very high, scalable. Then CP router receives tunnel packet, and it just remove IPv4 header. Because it is tunnel solution, you don't need to remake IPv6 header. So just send to user host. And second slide shows how to proceed outgoing packet. And we can say almost same thing with previous packet. It's also very simple. Okay. Then we can also use same way for the packet between subscribers. In this case, we assume destination IPv6 address is 2001 DB8 ABCD and XXXXS. It is destination IPv6 address, and CP router also extract second 32-bit of destination IPv6 address, then copy it to IPv4 header. So it's exactly same thing to packet outgoing to internet. Then it is just right. So I think 6LD may work well if your network is IPv4 only enabled network, and also you have enough number of global IPv4 addresses. And sorry, I made this slide in breakfast, so I forget one important point. Also, you should control. It is also important. You can control software of each subscriber. Software of CP router. It is another important point. Then if your network is already DSTAG or IPv6 already enabled, you don't need 6LD, of course. And also, if you don't have enough number of global IPv4 address, like mobile operator, 6LD works well. So it is also our another headache, but it is out of the topic today. So, sorry. So anyway, we choose 6LD for our ADSL access network. Okay, thanks.
So just, my name is Stephen Wright. This is some joint work with my colleague Barbara Stark from AT&T. Just by way of introduction, since neither of us are regular NANOG or ARAN attendees, both of us have been working on V6 in the groups like the Broadband Forum, trying to get V6 into things like residential gateways. And that's part of the rationale for this particular discussion today around address family translation. It's already sort of come up in some of the earlier talks that when you've got the v6 network and a v4 network, somehow somebody on one network is going to want to talk to the other, and that gets you into the problem of doing the translation. So in general, AFT is all about NAT. It's all about doing this address translation between a v4 address and a v6 address, as opposed to, I guess, the traditional NAT, which is from private to public within the v4 space. Okay, so there's some work in process on this, getting this standardized at the IETF, particularly in the Behave working group. There are working group drafts on NAT 6.4 and some work on NAT 4.6. And as you think about this as a mass market service, you start to realize you need more than just the NAT piece. You need the DNS piece to do the lookup as well, and that's also in process. So to go through an example of the NAT 6.4 case, NAT 6.4 is basically where you have a v6 client trying to get to a v4 server. There are working group drafts on this in the Behave working group. Basically, you have a DNS lookup through the name server that gives you back the DNS. So through that DNS 6.4, it gives you back the v6 address of the v4 server, and then you can do your normal TCP connect type messages through the NAT 6.4. What's not necessarily obvious on the figure is that there has to be some coupling between the DNS 6.4 and the NAT 6.4 implementation, because the DNS has to be able to calculate the v6 address that the NAT is going to use for the translation. So you've got to do some carefully coordinated configuration of the equipment or some other more proprietary mechanism to make sure that stuff stays in sync. So the NAT 4.6 case is exactly the opposite. You've got a v4 client trying to get to a v6 server. I didn't go through the detailed translation example here just because the 64 case seems to be a little more likely in the near term than the 4.6, because I think in terms of the number of servers on the internet, there's far more v4 servers out there than v6 servers. So. Issues with address frequency translation, it's basically a form of NAT, so all of the regular NAT issues that you've heard of, no, love, etc., NAT traversal, IP masquerade, IPsec issues, they all still apply. Anything with double NAT probably still applies. Anything with NAT 4.4, 4.44, 4.4, 4.4, however many variants you want to go through, that probably still applies. And you add a whole new set of problems because now it's not v6 end-to-end, so essentially the v6 stuff is potentially broken as well. But as long as you stay to the specific scenarios that are within those Behave drafts and just do the client to server through one single AFT translation box, that scenario should work. If you start to get more complicated and have multiply connected hosts, there's a whole slew of issues there because that, and I just refer you to the drafts to go into those things. So if it's all so painful to do this stuff, why bother? What's the point? Well, the point is that there are likely to be devices that really do give you this need. Many mobile devices, many mobile networks, these little iPhones and other things like this, there are likely to be cases where there are devices that will only support v6 addresses. So as soon as you, and the reason for that is basically power limitations, not so much the compute limitations, it's power limitations. They don't want to have more running than necessary on the mobile devices. As soon as you've got that, you've got a v6 only device, and you want this v6 only device to connect to the rest of the known public internet, which means you've got to get back into the DNS 6.4 and NAT 6.4 case. The next one that's maybe not quite so obvious, when you've got your mobile device and you have your dual stack infrastructure, whether it's dual stack through DS Lite or dual stack through 6RD, you get dual stack all out to the residential gateway of the home network. You've got dual stack running in your home network, and you've still got your v6 only device that you somehow need to connect to your PC and your printer that's still running v4. You know, you may have your Windows 98 machine that's still in the back basement doing whatever. You need to be able to print to it, connect to it, whatever. So all of a sudden, you need ways to get from this V6 device to a V4 device inside your home network. So there may be some pressure on some ISPs to support that function in their residential gateways or not, and that's going to be a business decision around how easy it is to upgrade those devices, whether that's feasible, whether it's a software upgrade, whether it's a new box that has to be shipped, and so forth. So in conclusion, the two examples I gave were both for the NAT64 DNS64 case. The NAT46 seems to be both less mature. The work at the IETF is still individual drafts rather than working group drafts. The NAT64 and DNS64 are internet drafts. There are working group drafts that are pretty far along. I think the DNS64 is a working group draft at about Rev 10 at the moment, so that's starting to get close to turning into an RFC. The NAT46 case just seems a little less likely to be needed in the near term as well, so just because there's more V4 servers out there in the world, in the wild. So in conclusion, while there are places where I think AFT may be a part of the solution, it's certainly not a panacea, and you're going to need V6 out there to make a more successful consumer experience. But this is still going to be a necessary piece to make a viable consumer experience. So, thank you.
We have a few minutes remaining intentionally, so lots of different possibilities presented here. We would love to entertain questions about any of the transition technologies displayed here. Operational considerations, I should have mentioned. We have a panel following us that will be describing some of the operational considerations for these technologies. Yes, sir.
Martin Levy from Hurricane Electric. As much as there's an operational panel afterwards, I'd still like to know from these participants and speakers performance issues, because what this has done is laid out very clearly the different protocols, pluses and minuses. But really, I know the operational side has been very much left aside from this discussion. And I wonder if it's possible, even from this point, just to have a quick word from anybody who wants to talk about that.
But the first thing I can think of is any of these solutions, if you put a box in your network someplace that is not the optimal path, which if it's in your core network, it's not necessarily going to be optimal path for all traffic, that's going to add some latency. And then anytime you add a box, that's also going to add a little bit of latency. So exactly how much, your mileage will vary depending on the box and where you put it. Anybody have any further comments on that one?
I guess the other point is redundancy, particularly with the NAT translation functions. A lot of these tend to introduce a single point failure mechanism somehow. That's probably even worse as you get towards the CPE implementations as opposed to things that are in the carrier network somewhere.
Andrew or Leo? Leo.
Leo Bicknell, ISC. Very interesting work here, and it's nice to see that we're getting the IPv6 transition stuff further into the home. But there seems to be a bit of a missing piece to me, and I'm hoping that some of the panel can address. The current work seems very concerned on getting down to the home gateway level and figuring out how to continue to make legacy v4 devices work behind that. One of the concerns that I hear over and over about that is people aren't generally worried about someone's Windows box or Mac being able to do v6 at the appropriate time. There's a lot of worry about these embedded home, consumer electronic-y kind of things. And I find that very interesting myself because, just to pick on a random example, with, say, a PlayStation or an Xbox, they already have a mechanism because people hack them every Tuesday that when you turn it on, it says, I'm not going to allow you to do anything until you do the mandatory upgrade. And I'm wondering if any of these large providers have actually gone off and talked to Sony and Microsoft and various people who make these things, the TV people, all the internet-enabled TVs. It seems like that as a way to avoid having some of the performance issues and other stuff with your transition technologies, a piece of the transition strategy is to work with those people to push native IPv6 around the same time you enable. And so I'm wondering if anybody's working that angle of it and trying to work more of an administrative transition technology as opposed to a actual technical one.
I have personally contacted people at Nintendo, Sony, Microsoft, and TiVo, for instance, to talk about when they will have IPv6 support in their boxes, and they've asked me when I need it, and I have told them. And I point to sort of the standard online, here are the standard crystal balls, and you know how reliable those are. All of them have said, okay, yeah, maybe we'll think about it someday, don't see any particular urgency. I have also working with a couple of venues to bring some of those kinds of companies into a room to give presentations, maybe a little bit more time than this, to talk about what the requirements are, why they're there, and what happens if they don't do anything. Any help with that? I certainly think this is a community that should be able to exercise some support in making those kinds of things happen. As far, and you mentioned PCs and Macs, and yes, we know that those operating systems are capable of supporting IPv6, some versions better than others, and so at least there we have mechanisms. And I agree that the consoles do a pretty good job of pushing updates. So I think that is a better solution than any of these. Yes.
And I want to add on this is we actually do in parallel. So we actively talk to the equipment vendors to support IPv6, but at the same time that we also have to preserve the investment from the home, so they already have it. So we're not saying that, okay, yeah, we can help, we already have a technology which helps the legacy equipment, so you don't have to push IPv6. It's totally wrong. So we are saying that we want to do it in parallel, but we just want to make sure that we have to preserve the investment for the current existing equipment, and that's it.
I will echo that is my biggest concern as well. And just trying to get the consumer electronic industry to understand what's coming and how they need to react is a big challenge. So I think it's amazing. One of the things I found out is the power of Best Buy in this debate. Until they actually ask for something, things just don't get implemented. So we might actually need to go that route versus trying to go directly to the source.
Andrew Dahl, Cascadio. One of my big concerns is that transition technologies turn into becoming the status quo. And the biggest concern that I have with the ones that we talked about this morning is the quad NAT, and how that could very easily go from being a crutch that we use to deploy IPv6 to something that basically prohibits IPv6 from actually making it into the network, because it's just so easy to do large-scale NAT everywhere. And we'll come up with new tricks that make UPnP and all those other things work, and there'll be new technologies to make things work through multiples and multiples of NATs. So I would like to, pepper the panel a little bit about what kind of things do you think that we can do to prevent these technologies that are available, and specifically quad 4 NAT, to prevent it from being a crutch that we use for 10 to 20, 30 years, rather than actually doing the work that we need to be doing to actually make the hard architectural changes to get ourselves into a better place, rather than continuing on the old way of doing things.
I can start on that one. So at least in my experience, the experience between native v6 and natted v4 isn't the same. So if you can't offer both, there's definitely a perception. The user will be able to see a clear differential between those two services. So I think that'll drive, especially if you're talking about native v6 plus NAT, dual stack model. I think you'll see that drive toward v6 just because people are going to expect a better experience than what they're going to get on the other side.
And one thing I also want to add is in different countries, they may have different deployment models. So I think in some of the growing, developing countries, they may have a higher demand for the IPv4 addresses and they cannot do it immediately. So the bottom line here is any technology we're deploying here, we call it transition technology. We try, because there's a cost hidden to deploy this and we are not making any revenue from it. So we are pushing very hard for IPv6.
Yeah, I think you touched on the key point right there is the operational overhead for this is quite large. So it's not something you're going to want to do for the full set of your customers. I surely wouldn't.
I think the real answer is that as long as the end user transaction is still a V4 to V4 thing, then the ISPs are basically pushing on a string. We can get dual stack out there, but until you get the content on V6 servers and you get a real V6 web that end users are trying to get to, we're stuck in transition.
Thanks. I appreciate the conversation. It's fantastic, but I need to close the mics because we're a couple minutes over. But go ahead.
Owen DeLong, Hurricane Electric, and just to further address Andrew's question, all of these transitional technologies come at such a high operational cost and with so many trade-offs in the user experience. I can't imagine wanting to live with them long-term at the carrier level, at the subscriber level, at any level. I just can't imagine anybody wanting to keep these deployed any longer than absolutely necessary.
I would go to great lengths to avoid using any of them.
My last comment here is we cannot do it alone as an operator. If like all the content providers, all the equipments, whether they can work with us together to push their equipment to IPv6, because in the end is from the user perspective, they don't care is V4, V6, all they care is services. If we can provide, as a community, provide better services to the user over IPv6, then this will be successful.
Okay. Thank you all very much.